If you have any problems accessing the link, let me know. I just want to at least spend the next 15 minutes recapping and then moving on from the last time. So let's briefly recap what we did. So what we discovered was that the general rotation operator can be written as the exponential of the sum of antisymmetric matrices. So let me just write it down schematically. The sum of antisymmetric matrices. I'm now talking about the rotation. Let's start with the rotation of matrix itself. Okay, so R is the rotation matrix. And the generic one is the one with the exponent being a superposition of antisymmetric matrices. And what we discovered was a way to write down the basis, right? So the basis, in fact, can be written down basically by just enumerating the non-zero, the independent components in the upper triangular part of the X, right? So it's 0 on the diagonals, and so if you pick 1 on the first entry, and this would be -1, and everyone else would be 0, and then if you keep going, 0 on the diagonals, and then 0, 1, and then this would be 0, -1, and so on. Actually, let's do the 3D example. So we did a 2D case. So if you do the 3D case, it will basically look like this: 0, 0, 0, 1, -1. Everybody else is 0. And then you have 0, 0, 1, 0, 0, -1, 0, 0, 0. And then the last guy is this guy, right? 0, 0, 0, 1, 0, 0. This is -1. And so on. And so, for example, let's pick this guy. What we discovered was that essentially we did a 2D case. Right? In the 2D case, we discovered that, for example, e to the minus theta of -1, 1, 0, 0, in fact gave you the rotation matrix cosine theta minus sine theta, cosine theta. Okay. And so basically you can guess what's going to happen to these three guys as well. And let me write it down. So this is 2D, 3D. You can write down the exponential of minus theta of 0, 1, -1, 0, 0, 0, 0, 0, 0. So if you know your linear algebra, then you know that the having a non-zero component only in these two components means you're only mixing the 1 and the 1 and the 2 axes, because you only need to care about this block essentially. Okay, so what it means is basically this will give you essentially this answer, but because we now live in 3 dimensions, so you have to be careful to remember the other dimension, namely the 3rd dimension. But this is the answer: 0, 0, 0, 0, 0, and there's a 1 here. Okay. You just have to remember you're not touching the 3rd axis, but you're just mixing the 1-2 plane essentially, and that will bring me to the next point. So e to the minus theta, and then this is 0, 0, 1, -1, 0, 0, 0, 0, 0, will in fact give me, now you're mixing the 1 free plane, right? So this is the first row, 3rd column, this is the 3rd row, 1st column. So what this is going to do is, if you think about what this linear operator is doing, is mixing the 1 and the third coordinates. And so 1, the first row, and the third row. 0, 0, 0, 0, 0. That's what's going to happen. Yeah, this is, if you like, you can think of this as there's a relationship between this guy and mixing. So what does this guy do? It acts on the third. Yeah, you see the third. It acts on the third axis and returns you the first coordinate. And then this guy, what this guy does is acts on the first coordinate and gives you back actually with a minus sign. This is what this operator do. Okay, if you know your linear algebra, this is what it does.
Is there one in the second?
Oh, thank you. This is it. Thank you. Yeah. I just did what I said I shouldn't do. I don't forget about the second axis, and I did it. I would, yeah. Okay, and then the last one, to the minus theta of 0, 0, 0, 1. Oops, yeah, 1. And then minus 1, 0, 0, 0, 0. And then finally we have, basically this is a mixing of the second and the third coordinates. And so you have 1 cos theta minus sine theta, cos theta sine, oops, cosine theta, this is sine theta, 0, 0, 0, 0. So what this does is it teaches us something. And this is very generic, right? Because as we say, we can keep doing this to any dimensions. So what you discover is that, in fact, rotations really involve a plane. Right? They don't tell you this in introduction to, say, quantum mechanics, or classical mechanics. Right? Usually you're told, when we rotate, we specify an axis and an angle. Right? How much you rotate, and you specify the rotation axis. And this is true really only in three-dimensional space. It's not true in any other dimension. So we'll come to this interpretation of having a rotation about an axis and an angle. That this way of describing rotations, we'll come to that in a little bit. But it's really not true other than in three dimensions. And we can see this, and we can see that actually the correct interpretation, the more universal, I don't want to say it's not correct at all. It's true in three dimensions, but in the more universal way is what we're seeing on the board here. You see that what you're always doing, for example, in 3D, this mixes the first and the second, this mixes the first and the third, and this mixes the second and the third. So you're always rotating a plane. You pick two coordinates, that defines a plane, and what you're doing is you're rotating that plane. Right? So this is something that we're just talking about geometry here, but it's worth highlighting, because otherwise what I'm about to write down can be a little bit confusing. So maybe I'll write it down in the words first. And there's something, so as I've explained before, I'm doing this as a warm-up to the Lorentz and the Poincaré group. So, what we're going to discover when we talk about the Lorentz group is something similar will happen as well. So similar rotations is part of the Lorentz group, but there's also the boost, as you guys probably know from special relativity. And in the boost case, you should also think about that as mixing mixing a plane, right? We're sort of rotating. The rotating is not quite the right word here, but really boosting a plane, right? What's the plane? Is between time and one spatial coordinate. You're going to start hearing me complain about whiteboards. Have I started complaining about whiteboards yet in this class? Yeah, these guys will know me very well. Start. You see, I cannot ever erase my whiteboard properly, and is that erase that spray thing anyway?
Yeah.
There is. Oh, this one. Thank you. Yeah. I don't like whiteboards. You guys are going to hear me say this again and again. So pardon me. I'm going to say it many times throughout this semester. And you take another class of mine, you're going to hear me say it again. I've been saying it for 5 years now. There are no blackboards in this building. Okay, anyway, so let's write it down. Rotations really act on a 2D plane. Like for example, e to the minus theta of, let's just pick one, right? 0, 0, 1, minus 1, 0, 0, 0, 0, 0. This rotates the 1, 3 plane. And only, so my claim is, this I have not shown. Right, so this assertion I've just shown because we have enumerated the basis for antisymmetric matrices. And what it turns out is it rotates the two axes whose components are non-zero in the generators, in the exponent. So the claim is that only in 3D can rotations be interpreted as acting along an axis with some rotation angle. Okay. We'll come to this in a bit. But now, so is that our alert? So we're supposed to hide the table, I suspect. Okay, so we'll get to this in a little bit. But now what I want to do now is to repackage this expression a little bit. Right? So remember, we're going to sum over all such antisymmetric bases. And so what I'm going to do is I'm going to denote it as J with two indices. And as you may guess, the two indices here, in fact, can be viewed as the non-zero entry. So maybe I'll write it back. So the 8th row and the B column is the entry with 1. And of course that means that the B row and the 8th column is the one with -1 and everything else is 0. by everything else, I mean every other entry is 0. So if you adopt that definition for the antisymmetric generators, what I'm going to do is I'm going to multiply by I, and this will turn out to be Kronecker A, and so, if I ask what is the n component of this, it will turn out to be the following. So I'll write it down and I'll explain what I mean. There's a few things going on here. So number one, my square bracket means anti-symmetrization. So it means I take mn and I'll subtract, because there are only 2 of them here, I'll subtract the pair swap with the minus sign, so that it is anti-symmetric. So this is a definition. So there are a few things going on here. So I'm now starting to use index notation. So I better explain a little bit what's going on here. When I write some quantity with some subscript and n, and there are only 2 indices as a warm-up, sometimes there'll be more, right? So it gets a bit more cumbersome to deal with. But with guys with 2 indices, you can always think of it as a matrix. So n is like a row number, and n is the column number. In this case, AB is really a label for the generator. So it tells you which generator, which basis antisymmetric matrix you're referring to. Right? And so it is this I times the J that actually corresponds to the basis antisymmetric generator. The reason is that when I put in this I, so that J, so reason for the I, is so that J becomes permission. Okay? And so let's take, for example, this guy here. Okay, so I claim that this guy would be, so for example, 0, 0, 1, 0, 0, 0, minus 1, 0, 0 is in fact I times J 1, 3. Okay. So as I said before, AB is supposed to tell you which component is the 1. And then once you determine it, then the rest is fixed, right? So number 1, everybody is 0 except the guy that's diagonally across, which is fixed because it has to be minus 1. But now, let's see what happens when I multiply both sides by minus I. Right? So J13 is actually now minus I times 1 minus 1, and everybody else is 0. So what you see is that the matrix, if you didn't put in a minus I, is antisymmetric, as we have said repeatedly now. But now with a minus I, we can now consider what happens when I take the dagger of it. So dagger means, remember, you take the complex conjugate of it, and then you take the transpose, or vice versa, right? The two operations do commute. So if you take the transpose, you get basically itself. But then when you take the complex conjugate, minus I becomes plus I. Sorry, transpose gives you, let me do it one step at a time. The transpose gives you a minus sign because the matrix is antisymmetric. But when I take the complex conjugate, now with the minus I, it will give you an extra minus sign, so it will actually cancel the first minus sign that I get. So which means that the inclusion of I, as I've said, really does give you a J that is permission. So if I do that, then what you notice is that all my, if I look at a single anti-symmetric basis, then all my rotation matrices can be written down as e to the minus I theta j, JAB, right? And this would be rotation of the AB plane. Remember, rotations really refer to, for a single antisymmetric generator. By the way, I keep using the word generator, and nobody asks me, what are you talking about? So J is the generator. In other words, not the guy that is antisymmetric, but the guy with the minus, with the minus I included, right? So J, AB, which are still they're still a basis, right? So the set are called the generators. They're the generators of rotation. And the jargon is just because for very small angles, you can, let me do it. For very small angles, physicists like to do this. I think mathematicians get a little bit pissed off when we do this because there's no longer a group element. But anyway, so if we do a small angle, then this sort of generates a rotation because the first order correction is in fact proportional to J. But anyway, so this is in fact now our form of the rotation matrix. And in fact, if you keep going, you will see that, as you recall, we said that X, the exponent, is going to be sum over all these guys, right? So instead of using theta, now I'm going to actually use omega, and I'm going to use omega such that I'm going to assume that these are anti-symmetric. They're really just rotation angles, as you can see. The direct correspondence is that this is rotation angle on the AB plane. But now if I were to superposition these guys, I need to write it in a form that allows me to use this, exploit this index notation. So let me write it down, and then we can discuss it. So it's going to be minus I omega AB JAB. And so I make it anti-symmetric because this guy is also anti-symmetric. So I didn't quite say it here, but I did say that MN, because it's the indices of the matrix, and because the anti-symmetric, because the generators are anti-symmetric, so MN better be anti-symmetric. But by construction, you can easily show, you can in fact see, that if I swap MN, it gives you a minus sign, because this gives you this, and this gives you this with a minus sign. But so will you get a minus sign if you swap AB. So if you swap AB, you'll get this, you will basically get this term, and this term will become this term with an overall minus sign. So it is simultaneously anti-symmetric in both AB and NN. Okay? And so this explains why I do this. If I sum over something that is symmetric, then you will find that the symmetric part will drop out because this is anti-symmetric. It won't matter, in other words. But I have to be careful not to double count, right? So the independent indices here are the upper triangular ones. So I actually need to divide by 2 to avoid double counting. So this, in fact, is a superposition. This sum is a superposition over all the generators, or basis generators. And now I can say that the general rotation is therefore e to the minus I over 2 omega AB JAB. So the final remark I want to make about my index notation is that, actually two final remarks before I talk about the Lie algebra, is the following, that whenever I have a repeated index, so remember AB refers to the coordinates that I have in my space. So AB will run over 1 through however many dimensions I have, say D, right? So whenever I have a repeated index, I will assume, unless I tell you otherwise, that it's sum over. So omega AB, JAB means I sum over A from 1 to D, and I sum B from 1 to D. But because otherwise there will be many, many summation signs, usually we drop it. The other thing I want to say is that I will usually use the notation where my English alphabets run over spatial coordinates only. And then later on we're going to do special relativity where there's now time. Right? And certainly in quantum field theory, there's going to be time. So time will be the zero component. In older books, sometimes you see time being the third component, the fourth component. So this runs from 1 to D, and later on mu, and so on, alpha, beta will run from 0. And usually we'll stop at 3. This is time. But in the older books, sometimes they put it, if you only have 3-dimensional space, sometimes they move 0 to 4 in the older books. But I think increasingly it's less and less common. But I thought I would say it here. I'll say it again when we do space-time. Because when we do Morentz and Poincaré transformations, Morentz transformations in particular, this will look almost identical, except now AB will become alpha, beta, alpha, beta. But I will, of course, have to explain what those guys mean in that context. But then you will see why this is a warm-up to that discussion. Okay. Any questions for me at this point?
I have one.
Yes.
Can you explain again why the superposition is negative?
I put out, remember what I did was the following, yeah? So X originally was a sum over antisymmetric guys, right? So let me just write it down, right? A sum over antisymmetric guys. And what I did was basis. What I did was I stuck in an I here because I wanted to call this guy Hermitian. I wanted it to be Hermitian. So because I stuck in an I better put in a minus I out here. And so that's accounting for this guy.
Oh, okay.
Yeah. I think I said it somewhere there, but yes, thanks for asking. Yeah. Whenever it's not clear, ask me. Hermicity is important also. Yeah, in fact, you should ask me, so why do you bother, right? Why make it Hermitian? At this level, of course, it is just semantics, right? Because after all, the combination is still the same thing. But the reason why we make it Hermitian is because we want to do physics. Right now, we're just doing geometry. And in physics, the generators, once they become Hermitian, once you can identify them with Hermitian operators, then they become observables in quantum mechanics. Okay? right? But I want to do it slowly, but essentially that's where we're going. I'm going to make contact with what you learn in quantum mechanics. Then we'll go on to do the Lorentz group. So it's a warm-up, as I mentioned. So, okay, but before we get to quantum mechanics, I now want to talk about group multiplication. And this is where the concepts of the Lie algebra comes in. Group multiplication and Lie algebra. So I mentioned this the last time, that because our exponents are operators or matrices, it's not true anymore that you can just combine, you can just add the exponents when you multiply these guys. So specifically, this is a rotation, this is a rotation, and we expect a rotation, right? Is a group. In fact, we don't even have to use the word group. You know that rotation is something intuitive enough that you know when you rotate and then you rotate again, it must be a net rotation, right? But to compute that, it's not just the exponential of the sum of the exponents, right? Because and this is the key point, the commutator of x and y is not zero. They don't commute, right? Matrices don't commute. So that's actually the key problem. It's a problem, and also it's going to give you the key feature for why we have something called the Lie algebra. So, but we do know what to expect, right? So we know that x is a sum of anti-symmetric guys, and so is y. So what does that mean? It means that if we know that rotation is a group, that means that it must give you an exponent, but now the exponent itself must also be a sum of anti-symmetric generators. Same thing, right? So even though I don't know what the explicit form is, it must be that if this is a group element as well, it must be a rotation for the case at hand. If these guys are rotation, this guy must better be a rotation, and therefore that means that y, if x and y were a superposition of antisymmetric guys, z better be also an antisymmetric guy as well, sum over the generated the basis. But how do you guarantee that? Okay, and this is where we need to invoke a result called the Baker-Hausdorff